Hello, good afternoon.
Good afternoon, Professor Gokhale.
Yeah, nice to see all of you.
Good afternoon, Professor Gokhale. Sudhanshu here.
Good afternoon, Sudhanshu.
Yeah, same room with Amrinder Singh, so you can't see my face.
Okay. Okay, we were just discussing about the book that you are co-editing, so please follow up on that.
Yeah.
Yeah.
It's on Zoom. Okay. You can come here and see. I thought that I will take my lamp. Yeah, it is. Need something to take notes of.
सिस्टम देखिए हाँ पहले उसको ये करता है म्यूट कर लेते हैं
Professor Singh, Bala here. Can you hear me?
Yes, I can hear you, Dr. Bala.
I'm on a slightly weak connection, so I will not switch on my video.
That's fine.
Okay, thank you.
Good evening, everyone.
Good evening, Professor Mazumdar.
Yes, Professor Gokhale, very good evening indeed.
Thank you for agreeing to give this seminar today.
No, my pleasure. And it's nice to see you. Though,
Okay.
not physically, but
Yeah.
your smiling face is it brings a great feeling.
Thank you. Thank you.
So, we are going to start.
कहाँ गया?
So my request to all of you is to kindly mute your audio for the duration when we have the talk going on. And during the question answer session, you can put your questions in the chat box, and then we will put up depending on how many questions we can take. So formally, I would just start now. Good evening. I am A.K. Singh, Chairman. I am Kanpur chapter. It's a great occasion that today we are going to have our third IIM Platinum Jubilee lecture series to be delivered by Professor Dipak Mazumdar. And on this occasion, I welcome all of you on behalf of IIM Kanpur chapter. It is great honor for us that Professor Amol Gokhale, President IIM, has agreed to grace this occasion, and he is the chief guest. So before we go for the introduction of our lecturer for the day, I would request Professor Amol Gokhale to say a few words on this occasion.
Thank you, Professor Amarendra Singh. Good evening to you. Good evening to Sudhanshu. Good evening, Professor Dipak Mazumdar, Professor S. Basu, several other senior people I notice here, students. I have not been careful in seeing the list of participants, but I can see a galaxy of people attending here, and above all, Dr. R. Balamurli Krishnan, Bala, who is the convener of this IIM at 75 webinar series. I'll just say a few words before we go to the next part of this evening. So as you know, on 24th of February this year, our institute celebrated its platinum anniversary. That is, it completed 75 years of its contributions to the nation in the field of the metallurgical and materials profession. So every time we celebrate, every time and a professional body completes such kind of years, 25 or 50 or 75, it's the time to take a look back at the past, see what the institute has done in terms of serving the profession. Also look at what happened in the profession in general, no matter whether it was done through the institute or not. And also break new ground, start new activities, etc. So in that spirit, we launched several activities which were announced on 24th February in the gracious presence of the Minister for Steel and Minister of State for Steel also. We are going to publish a book called Indian Metallurgy, the Platinum Years, with several invited articles. Several people have already agreed to write articles which will cover what happened in metallurgy since 1946 in Indian industries, research institutions, academic institutions, government bodies, and also some of the individuals who have been leaders in metallurgy, very senior people in the profession. Other than that, several other schemes were also launched. I think Secretary General, I saw in the program that he is going to say a few things about the Platinum Jubilee different programs. So IIM at 75 webinar series is one such idea that we have been implementing, where every month at least one or two, at the most two seminars are being held. Dr. Bala will correct me, but I think it's probably the fourth one we began by the webinar conducted by Bhubaneswar chapter, and then we had Kolkata, and then Delhi chapter, and today it's the Kanpur chapter. Since the webinar is in connection with the Platinum Jubilee, we look forward to have talks which are not very specific research conducted by the individual, but talks which either are overviews, which cover important areas, or talks which take us to the edge of knowledge in a particular area, or talks which are thought-provoking, or which provoke our mind in certain direction. So the very first webinar by Professor Samit Rai of NCBS, it took us to the edge of knowledge in the field of material science, a particular area. The webinar which took place 10 days back, which was on strategic steels, its evolution and progress and the current status, gave us a very good overview of what happened in the field of strategic steels. Many of us became nostalgic, those who have been tracking the field of strategic steels in the R&D sector at least. And it gave a very good picture to even a newcomer what has been happening in strategic steels. Today's talk, I think it addresses the third requirement of such talks that I mentioned, talks which are thought-provoking. We have some premises based on which we pursue our careers. We have some assumptions which, unless somebody challenges them, our mind doesn't think that things may be different. So today's talk, I think, is one of those exciting talks, going by the title of it and knowing the speaker who is going to talk on it. So we have Professor Dipak Mazumdar, who is a well-accomplished teacher and a researcher in the field of steel metallurgy. Not only that, he is very intimately connected with the Indian Institute of Metals, the Kanpur chapter. He has got several recognitions from the institute, apart from other professional bodies that may be said in his introduction. And the topic that he has taken today, the role of basic research in steel plant R&D, is indeed a very thought-provoking topic. Not to mention its relevance to the Indian industry all along, and especially today when India has taken the position of second largest steel producer in the world. And if we want to become the largest steel producers, not just that, but to make technology-driven high-performance steels, then I think the role of R&D can hardly be overstated. I may just mention lastly that the Honorable Minister wants us to do an event later this year which will address how the Eastern Indian states, Eastern India, can be made as a manufacturing hub. This particular region is endowed with raw materials in ferrous metals and materials, non-ferrous metals and materials, as well as strategic metals. And is very keen to see how value-added products can be made so that the country really gets a good control, a good sovereign control on the end products, and not just sell the raw materials, which is not really the best thing to do when the country has such a large intellectual potential resource in the country. So I think topics such as this give me the confidence that I think the event that we will do later in the year will be a good one with all the relevant people participating in it, and we should be then in a position to give a white paper to the Ministry of Steel in fulfilling their dream of making Eastern India a manufacturing hub in the country. Thank you very much for inviting me. I truly, as I said, look forward to this topic which Professor Mazumdar has chosen. I know him for the last several years, and we are good friends. I truly look forward to listen to him today. Thank you very much.
Thank you, sir, for your kind words and welcoming the speaker. I would now request Dr. Bal Murali Krishnan to throw some light on this monthly webinar series, and then we will go for the introduction. Dr. Bal Murali Krishnan.
Good evening, Professor Gokhale, Professor Amarendra Singh, Professor Sudhanshu Singh, Mazumdar, and everybody else. I'm on a weak connection, so I'm not daring to go through the list of participants. Neither have I switched on my video. I'm sure we are all in for a treat today. And it gives me immense pleasure that the Kanpur chapter is organizing this event. And Professor Gokhale was right. This is the 4th event. And first time, as we have planned in March, we are having 2 events. The like you mentioned a little while ago, the first one was on the manufacture of strategic steel, and it had speakers from both the steel manufacturers as well as the users of the strategic steels, and gave a very nice overall perspective. And today, I think we are in for a treat by through this talk by Professor Mazumdar, who's going to talk about the R&D and in the steel production and its role in steel production. I think it's very timely and interesting, and in some way it complements the talk that was happening that happened earlier this month. Very often people think that R&D and production are very different domains and operate in their own silos. And in my own work over the last 20 odd years, I've been trying to bridge this gap, but more from the physical metallurgy and treatment and that's standpoint. And I'm sure today, Professor Mazumdar, I hope, will show us how that the silos model is not the case, and there's a lot of interaction and overlap, and there's a lot that R&D can contribute to increase the efficiency of production. So I'm really looking forward to this talk today. And I just want to add that this monthly webinar series, which was planned basically from January 21 to February 22, that's a span of 14 months with a maximum of 2 seminars per month. And in January and February of this year, we had 1 each, and March is the first one that we have 2 seminars, today being the second one. And for those participants listening from other chapters, I would urge you to consider organizing one such webinar along the lines that Professor Gokhale spoke about under one of those 3 criteria. It should not be an individual's research work, but it should be either a broad overview or a thought-provoking talk or something that has a lot of general applicability. Okay. And the next 3 webinars being planned are being organized by Kalpakam, Jamshedpur, and Coimbatore chapters in the next 3 months. And so I'm looking forward to an excellent series overall, and in particular to a great talk today evening. Thank you, everyone. Processing, you can please take over. Continue the proceedings.
Thank you, Dr. Bal Murali Krishnan, convener. I am Platinum Jubilee monthly webinar series. Thank you very much. Now, I would take this opportunity to as Professor Gokhale mentioned, to the Indian Institute of Metals community. Professor Dipak Mazumdar does not require any introduction, nor to the academic world and the iron and steel fraternity at large. However, as is the custom, it's my duty and privilege to read out a brief introduction of Professor Dipak Mazumdar, who has very kindly agreed to deliver a talk in the IIM Platinum Jubilee monthly webinar series. Professor Dipak Mazumdar graduated in metallurgical engineering from the Regional Institute of Technology, Jamshedpur, and subsequently obtained his master's degree in metallurgical engineering from IIT Kanpur in 1982 and PhD in process metallurgy from McGill University in 1985. Following his PhD and postdoc at McGill, he returned back to India and joined IIT Kanpur in 1987 as assistant professor, where he rose to the position of associate professor in 1993 and to full professor in 1995. He also served as the head of the Department of Material Science Engineering Department at IIT Kanpur. He has been visiting scientist and professor at McGill University and University of California, Berkeley. He has over 160 publications in reviewed journals, and also has written 2 books, Modeling of Steel Making Process and a first course in iron and steel making, which is widely recognized as the textbook for this subject. Professor Mazumdar has received numerous awards and accolades for his seminal contribution to steel making research and education. I would just mention a few here. He received Kamani Gold Medal of IIM in 1990, International Scientific Exchange Award, NCERC Canada 1992, Metallurgist of the Year Award from IIM in year 2000, and the SAIL Gold Medal in 2001, 2012, and more recently in 2020 from the Indian Institute of Metals, the GD Birla Gold Medal from IIM in 2009, and the coveted INE Chair Professorship in 2011. He is a fellow of the Indian National Academy of Engineering and the Indian Institute of Metals. Professor Mazumdar is also on the editorial board of MedTrans B and Transactions of IIM. He has collaborated extensively with domestic steel industries, of which we are going to hear today. And during the past decade, he has made several contributions to the industry in general. And he has also received WASPIC International Research Award in 2010, which is given for the contribution to the domestic steel production sector. Professor Mazumdar was holding the Ministry of Steel chair at IIT Kanpur during 2012-2017 and has been a recipient of the Distinguished Industry Professor 2013 from the Indian National Academy of Engineering. For his sustained contribution to the teaching, ethics, and research, Professor Mazumdar received the IIM Distinguished Educator Award from IIM in 2014, as well as Outstanding Teacher Award 2015 from INAE. More recently, in 2019, Professor Mazumdar has been honored with the National Metallurgist Award from the Ministry of Steel, Government of India. With these few words, I now invite Professor Dipak Mazumdar to deliver his lecture on the role of fundamental research in steel plant R&D. May I request all of you to keep your questions to the end after the lecture is over. So, Professor Mazumdar, kindly take the floor. Thank you.
Good evening, everyone. I would at the outset thank the IIM Kanpur chapter as well as the Indian Institute of Metals for giving me this opportunity to speak on a topic that is so close to my heart. And I'm humbled by the presence of the president of the institute itself, Professor Amol Gokhale, and many of my friends from the industry, 25 years old friendship. I could see Mr. Parikh there, with whom I started to work in 2001 at Hospet Steel. And also there are many other friends and distinguished domain experts in the list of audience. So as I project my slide, and that's, I would like to say that this talk is structured in three different segments. And the three different segments are split over, sort of equal space or equal duration, 10 slides each, and I should be able to wind up in about 30-35 minutes or so. So this is the beautiful backdrop of the institute. I have projected throughout my life the institute's logo at the top, because it is this, the name of the institute, that has given me perhaps everything, including a holistic lifestyle in this wonderful campus. And you could see, one of my friends and our head of the department, the previous head of the department, not immediate previous, the Professor Sanjeev Bhargav, who happens to be more. And every time I project this slide, I becomes very nostalgic about him, my association with him. And I think I should, pay tribute to Professor Bhargav on this day, because I'm talking to mostly metallurgists, and Professor Bhargav being a very well-known friend of mine and well-known amongst many of you. So if I move on to the next slide, so this is the three segments that I was talking about. So I will address on our industry supported steelmaking research activity at IIT Kanpur, where I'll show, briefly mention that since when we started associating ourselves, which are the industries to which we cater, what are the subjects, what are the goal of the research, and so on and so forth, for about 10 slides or so. And following that, I'm going to discuss two problems very briefly. They're interrelated problems, and they're very pertinent because both of these problems are associated with steel cleanliness. And we all know that steel cleanliness is what determines the service life and is of immense engineering importance, as far as making engineering components are concerned. So these two problems, which I will not read here, you will see it, will be followed by an epilogue, and I will quote some, some memorable quotes from the literature, with which I resonate myself, and following that I will conclude the discussion. So our association with the industry started something around 2000. We were extensive, I would say, extensive interactions. So it is almost 20 years we have been working with the domestic steel, refractory, and ferroalloy industries, and in steel industries also. Among steel industries, we have worked both with integrated steel plants as well as the special steel plants, and completed projects till now in the last 20 years is about 26, as I have indicated, and the area of research that we have covered in our research and industry-funded research is BOF and EAF steelmaking, ladle metallurgy, tundish metallurgy, transfer operations, as well as ingot and continuous casting. So if you look at our major collaborators, and you can see that there are several steel plants. These are our principal collaborators. That means we have been funded by them with more than one projects. And for example, industries like Hospet Steel, as well as JSPL, Rashtriya Ispat Nigam, they have funded, I think, more than 4 or 5 projects each. And these projects were not only challenging, they are very creative also. And it is evident that, as I have indicated below the table, that actually 2 of the works culminated with SAIL gold medal, which shows that these are not mundane research actually. And of course, I do not have the time and scope to address each of these, but nonetheless, the 2 cases that I deal subsequently will give you enough indication that these are indeed doable problems, challenging problems, and at the end of the day, it is beneficial for both the professor as well as the industry. The goal of the plant research has been, because it's an engineering activity, and as I say, always I have been saying that engineering activities are concerned with wealth generation. And if the exercise fails in generating wealth, then it is a meaningless exercise as far as steel plants or per se any other industry is concerned. So, and because we are professors, we have to blend, this business goal with an academic goal, and then come up with projects which give us, particularly the professors community, that intellectual feed, which is essential for our survival. So we have, with a goal of enhancing steel mill production, steel mill performance, process performance more specifically, we have addressed, I think, projects related to different topics: yield loss reduction, product cleanliness improvement, process time reduction, process optimization, beyond yield loss, etc., and energy as well as material audit. So these were the major, basket in which the projects, and these are not designed by me. These were industry-driven projects. Actually, they, proposed the goal, and I had to deliver in a time-bound fashion. And you can see that those, I have put the logo of most of the steel industries with whom I have collaborated very extensively, and they both include, as you can see, primary, integrated steel mills, special steel mills as refractory mills as well. We have funded, we have done a variety of projects. These are all available in my website and the web pages. I do not wish to discuss each, even mention them. But the most distinguishing features of these projects, 26 projects that I have mentioned, that we have throughout applied, physical and mathematical modeling as the investigating tool. And in almost all cases, we have been successful in validating the model with plant scale data. So the plant scale trials were an essential ingredient of our research activity, because we realized that unless the model results do not translate to the reality, these exercises per se are meaningless as far as fulfilling industrial objectives are concerned. But apart from this industry-funded projects, research projects, I would like to also mention that we have trained more than 800 shop floor engineers through continuing education activities that I had in Kanpur. And this is, I think, a remarkable feat. I would consider this. I think it's a more, because as a teacher, I really enjoy delivering lectures before people who are working on the shop floor, who did not have a chance to see an excellent academic environment in an institute. And I could bring them over, the company funded them, spared them for 2, 3, 4 days. And you could see how many industries from the country, it's possibly the list contains almost all of the prominent steel makers, refractory makers, and design organizations in the country. So, and this is a great satisfying exercise beyond doing industry-funded research that we have been able to train and teach people on the on various topics related to steel making, be it oxygen steel making, lead metallurgy, flint steel making, and so on and so forth. And today, I am very grateful that industry has stood solid behind us in supporting not only the research which culminates into money, but they have realized that generating knowledge is very important. Training their manpower and keeping them right at the front is very important. I think professors like us have a great role to play as far as taking the Indian industry forward, so far as the knowledge bank is concerned. So if you now superimpose the people who have the industries or the people who have come to IIT Kanpur from different organizations, and if you superimpose this information on a map of India, you could see possibly, from throughout the country, people have come to IIT Kanpur to take advantage of the expertise that is possible, that is available at IIT Kanpur. So I feel really privileged that in the last 20, 25 years, the industry has stood rock solid behind my activities and have supported to a great extent, be it industry-funded research or be it continuing education activities. Now, although we have done a lot of these exercises, I must now mention that there are certain prerequisites in order to be able to fulfill the ambitions and aspirations of the industry. It does not happen spontaneously. And if you go to the next slide, we could see that we have for translational research, I say that knowledge of manufacturing, measurements and modeling we consider as a prerequisite or subject knowledge, which really is essential. And on top of that, if you have a good modeler or a researcher, not just one, as I'll show you in the subsequent slides. So it is very important to have the necessary knowledge base also, without which, I think there's some background. So the concentration gets disturbed, if you get some background, figure out. So, yeah, Professor Singh, could you mute everybody? So, industrial research per se, to do, translational research, I think a good knowledge base is necessary. And that knowledge base is constituted by knowing the manufacturing, the details of manufacturing, which is still making and allied subjects, having good idea about measurements because you have to carry out high temperature measurements, and also a reasonable expertise in modeling. And perhaps the inside of the modeler plays a great role here. And you have noticed that when Professor Singh read my biodata, he said that I joined IIT Kanpur in 1987, but the first industry-funded serious project started in 2001, which means that I had to get some experience. I had to lose a few hair or help turn my hair gray before the industry had to develop confidence on me. So that's what I said. With age comes experience, and that experience is very, very important as far as the insight of a modeler is concerned. And it is with the insight of the modeler with good subject knowledge. And if I show you that this is what it is, that you have good knowledge of manufacturing, you have the science base of steel making, thermodynamics, metallurgical kinetics, and fundamental. These slides I have shown in many places. And this knowledge base is necessary per se as a prerequisite for the researchers or the team of researchers. And I would say that if you sum it up, then you can say that you can do translational research, fulfill the ambitions of the industry and your own ambitions, provided knowledge, experience, adequate plant exposure, and a dedicated team is there. And without which, you will not be able to do any meaningful R&D that caters to design optimization control of steel making processes at the industry scale. So with this background now, it is worthwhile to look into the two problems But I would like to say, I would like to summarize here that we have been able to do a lot of industry funded work or work related to the industrial, production, etc. And the support of the industry is very important in this. And I think professors have a great role to play here. I think sitting in the office, I have realized will not bring any industry closer. And I think, once you start visiting the industry, be a part of the team. And that's how the confidence building starts. And that's how the industry starts to realize your abilities. And that's how the industry opens their door. And, I could, with their support only, and I could make the industry, steel industry, as a large full-scale laboratory for my research work. And it has been extremely gratifying. I would like to mention specifically at this particular moment. So I think if I don't acknowledge here publicly the support given by the Ministry of Steel throughout my professional career, the support extended to me by the steel and domestic steel and refractory industries, I would have been nowhere. So I sincerely acknowledge their assistance in shaping my professional career in this country. So with this introductory statement, now let us go back, move forward and go into the two topics. And these are the industry funded research, and I will explain. And they're interrelated, as I have mentioned. So the first issue is the assessment, or the topic is the assessment of steel cleanliness in Tandish. So I was trying to say, Tandish, most of you know, because I think the audience largely knows what is steel making. So you have the Tandish, which is the intermediate vessel, and you could see in the inset that you have a ladle, Tandish, and a mold. And this Tandish is an intermediate vessel. It distributes molten metal from the ladle into a number, one or more continuous plastic molds. In the Tandish, what happens is, because we don't want any atmospheric interactions, as transfer takes place, we transfer through a ladle shroud, and that's how we try to prevent air-steel interactions during the transfer process. But this shroud and the collector nozzle, which is shown here, and I will discuss this in a greater detail in the later slides. This is really because these are two refractory artifacts, one mounted on another. They are never perfectly sealed. So as a result of which air respiration occurs. And this gives us an idea of the role of air respiration during such transfer with leaking little shrouds. And you can see here, you can consider on this circle which I have elucidated or earmarked in all the figures. And you could see that there is a two-phase, there's a gas liquid region here, liquid and same is here. So huge interaction between the atmospheric air and molten steel is possible. And this molten steel is deoxidized. It does not contain much dissolved oxygen. So apart from when air ingression occurs, there's a reversal of flow takes place below the Tandish. But that's not what I'm going to talk about. That's not so important as far as cleanliness of steel is concerned. It has only secondary influence, but nonetheless, the buoyancy exerted by the entrained bubbles could disturb the flow that is evident and which has been captured very realistically by carrying out new method circulation. But that's not the entire story. Air ingression, when it takes place, then what happens, the oxygen from the atmosphere gets dissolved, as in the melt. And this dissolution is driven by a concentration gradient because atmosphere contains 1.21 partial pressure of oxygen is 0.21 atmosphere. And steel could be containing 10 ppm, 15 ppm oxygen depending on the extent of deoxidation. And the dissolved oxygen, when it exceeds a critical value, particularly in aluminum steel, it can react with alumina. And this is a solid product. And this solid product acts as an inclusion unless they are all moved. Parallelly, you have aluminium, dissolved aluminium, and if air ingression does not take place, then we have Tandish powder, which contains silica. Silica is a less stable oxide. Aluminium reacts with silica. There's a slag metal reactions, and as a result of which alumina is produced. So the alumina can be generated in steel, and as a result of which the cleanliness of steel can be impaired in the Tandish. So these are the reoxidation reactions. And as you can see here, I have plotted the industrial measurements, which shows that the VD lifting aluminum content is higher than the dissolved aluminum content at the solidified bloom. This axis is 400 and 400. This is 1:1 line. The points which are above the line essentially implies that we have more dissolved oxygen at the VD lifting station than at the solidified bloom, which essentially means that aluminum has undergone fading in the Tandish, or dissolved aluminum is removed from the Tandish itself. And how dissolved aluminum has been removed, it is by formation, through formation of alumina. Either of these reactions could take place in condition, as a result of which aluminum can fade and generate non-metallic inclusion, which can jeopardize the steel quality or increase, impair the cleanliness of steel. Now, so therefore we understand that Tundish is not an inert reactor. In Tundish, this sort of a reaction takes place. So per se, Tundish is a reacting multi-phase flow system, because we have gas liquid flows, because of air entrainment takes place, and I will show that air entrainment is very common in steel industries. It is not zero per se. So therefore, we can expect that air entrainment will take place, aluminum fading will take place. So treating Tundish as an inert reactor is a gross simplification. I think we are in 21st century, where steel making is 160 years old, and it is perhaps time to take into consideration the exact nature of the reactor in order to deliver what is required to be delivered. Now, most of the time, we as academicians, we have compared Tundish, it's a popular way is by comparing the residence time distribution curve, where we inject a dye, find its residence time distribution, get it done for two different Tundish designs, and then we consider, by evaluating this curves, that which Tundish has, a better intrusion flotation capability. But this is not right, because it does not capture one of the intricate features of Tundish operation, which is reoxidation. So therefore, my assertion is that you can get rough idea, but this nonetheless is not going to be the true picture, or it can be misleading also in some cases. Similarly, the cleanliness index in the steel industry, or flotation of non-metallic inclusion is determined by using this particular criteria. When we say aluminum insoluble, what aluminum means? It means Al2O3, which is solid. In the blue, divided by the aluminum insoluble or alumina content in Vd, which essentially means that if aluminum insoluble Vd is equal to aluminum insoluble bloom, that means no inclusion has floated and cleanliness index is equal to 1. But again, this has nothing to do with the reoxidation that takes place. So whatever the academicians have been doing, or the industry people have been adopting, to quantify the Tundish process performance are not adequate, and we require better criteria in order to quantify Tundish process performance, so particularly its ability to float inclusions. So, when you do Tundish processing, so what happens is, you look at the figure here, this is the dissolved nitrogen content in Tundish. So dissolved nitrogen at the Vd lifting station for two different grades are shown here. And as you can see that the lifting nitrogen, dissolved nitrogen content, as it goes, so this is the Tundish filling starts. It shoots up, and then it attains a steady state. So this is what I was talking about, that there's an air ingression taking place, because absorption of nitrogen essentially indicates that melt has come in contact with the atmosphere. So along with nitrogen, varied amount of oxygen will also get absorbed by steel itself. And parallelly, as oxygen gets absorbed, we can see this figure I have shown already, that you have aluminum fading from the steel and alumina generation. So now, if you consider this process of alumina generation, particularly for aluminum keel steel, carry out a simple high school level, 10th grade, 10th class material balance, you could very nicely find out three parameters. One is called the generation index, the other is called the flotation index, and the final one is called the total aluminum loading in the Tundish. The total aluminum, this is the total aluminum loading in the Tundish, and this is the generation of inclusion, because whatever dissolved aluminum has faded, this delta means change, has faded, that has manifested in alumina formation. Similarly, the flotation part is this particular component. So if you divide whatever is floated divided by the total inclusion loading, you get flotation index, and this indices vary from 0 to 1. And this gives you the total inclusion loading, where you can see this is the steel making component. This value will tell us how good has been our steel making process, and this will tell us how good has been our Tundish processing, and two together will determine the total insoluble aluminum content in Tundish, or the inclusion content, or the cleanliness, of total inclusion loading in Tundish itself. So you can, by measuring this, and as I said in the top of the slides, so if water model will not be able to capture the reaction part, and when you have new phases which are generated, that will also be not captured, adequately, because we require very sophisticated models, which can take into account, model across length scales, including nucleation growth and precipitation of new phases and so on and so forth. So perhaps, by measuring the changes in aluminum content, you could be able to formulate this criteria. And this is not just for aluminum. You can do it for magnesium, you can do it for calcium treated steel, you can do it for silicon, for anything which fades in tundish. You should be able to derive a similar kind of a criteria and then find out that, what is. So by evaluating this flotation and generation index, you will be able to find out that. And now you can construct parameters vary from 0 to 1, as I have indicated. So you have, a tundish top cut diagram, which is a tundish operating practice and cleanliness assessment diagram. And this represents, so it varies from 0 to 1. And this is the region, which is the desirable region, which is the region of low reoxidation and high flotation region. I will like to have all my tundish points coming into this particular box, which is number 2. And if you now plot, the industrial data from Indian steel plants, the figure is alarming. And you could see that only few, points fall in the, box number 2, and bulk of the points fall in 3, which is the region of high generation and high flotation, which tells us that the tundish is not working well, as far as reoxidation. So it is a high flotation is there, but high generation is also there. So that means the reoxidation is a big problem in Indian steel making system. This is again a very recent work which we have published in association with 6 different steel makers in the country. If you compare, for example, 3 special steel plants, and you can see among the 3 special steel plants, also there is quite a bit of difference. They have the same sizes, same capacities, but yet if you compare, total inclusion loading, it's a huge range, which shows that these steel plants are not able to control their process well. Otherwise, I would have gotten this value, in a narrow range itself. Okay, and similarly, these steel plants are relatively better than these steel plants, where we see that generation in the tundish is significantly higher. So we can draw a series of conclusions, from the formulae that has been advanced in this work. And I would like to now summarize that, by going to the industry, visiting industry, making industrial measurements, and invoking 10th level material balance with some process knowledge, we have been able to formulate a new set of quantitative criteria for assessment of tundish process performance. And this allows us to compare now realistically different tundish designs as well as performance of different tundish systems. And we can generate also, by looking at the value of GI and FI, we should be able to tell that whether this tundish is good as a flotation device or good as a, bad as a reoxidation. And then, we can take appropriate corrective measures in order to, come up to the expected level of performance from the tundish. So I will quickly go through the next part. So it is an interrelated part. Now we are looking globally at tundish. Now let us look at locally in the tundish, shroud and collector nozzle joint, which I have highlighted here. Let us look at what happens here. So this is joint between 2 refractories here. And this is the little shroud, which is mounted onto the collector nozzle. And you can mount it with a robotic arm, or you can have some kind of a manipulator, who can force fit the shroud into the collector plate nozzle and inject. What happens is, if you look at this joint, here there's a joint, and this joint may not be often perfect. And as a result of it, what you do, you inject gases here, and this gas tends to be distributed around the shroud collector nozzle joint. And this gas is an inert gas, and which presumably, will provide some kind of a shielding effect. And there are, as you can see here, this is the gas injection port. So this design, if you look at the little shroud gas delivery designs, this is an 8-port design here. So gas is injected here, gas comes out through these ports, and as a result of which there is a shrouding, or circumferential distribution of argon around the shroud collector plate nozzle. Similarly, you have, another design here, which is a metallic painted design, and you have a single discharge port with some kind of a, external groove, which allows argon to be delivered around the shroud collector nozzle assembly, so that you do not get air integration. If some gases go, and that will be argon, and that will not lead to reoxidation. That's a supposition. Let us see whether that supposition works or not, or it's legitimate or not. So imperfect collector nozzle little shroud assembly, if it is there, air integration is bound to happen. Okay, and nitrogen and oxygen pickup, as we have seen, in the case of aluminum fading graph that I have illustrated earlier, reoxidation that takes place. So this is the collector plate, collector nozzle, and this is the little shroud. It's an isolated one. Somebody is holding it. Okay, you don't see that person behind. So this is the nozzle through which gas is injected, and through this ports the argon comes out, and this shows the little shroud in operation in the steel plant. And this is a picture by which indicates how from molten steel from little is transferred into the continuous casting mode. This is a big slide. It contains a lot of data, but we did not consider everything. So these are little shroud data for 6 different steel plants. 3 of them are special steel plants. 3 of them are slab casting or integrated steel plants. Most important is that one uses no argon injection, the other uses argon injection, and the varied argon injection rates of argon injection are varied. They are not unique argon injection. Even among same group of steel industries, special steel plants, you can see the steel, the gas to liquid ratio or argon to steel loading ratios are different. And you can see here that different amount of nitrogen, despite this gas injection, whether there's no gas injection or varied gas injection, there is nitrogen pickup by steel, which essentially indicates that the shroud collector plate nozzle is really perfect in the industry, and therefore, some oxygen is going to go in, some nitrogen is going, and these are manifested consistently in the 6 different steel plants that we have considered. To verify this, what we have done, we have carried out, this is the work of my doctoral student, we have taken the cut pieces of little shroud of 3 different designs, and we have carried out dye tracer distribution by submerging the actual shroud heads in a water bath as it is indicated. So you have the potassium permanganate injection system. You can say that, sir, why you are using water as the fluid here, because it is argon gas, but we must understand that when you do simulation, if we maintain the inlet Reynolds number, whether it is air injection, water injection, or argon injection, if you maintain the similarity of inlet Reynolds number, then the curves overlap. Okay, the distribution of the gases or the liquid overlaps, as you can see here, which shows the distribution of water as well as air. So we understand that we have to maintain that Reynolds similarity so that we can legitimize this water model studies. But what it shows most interestingly is that as we have found out that the argon distribution is not all with one port system. No matter what the argon delivery systems are, the argon distribution is far from circumferentially homogeneous. This part does not get any argon injection, for example. Here it is somewhat better, and here it is still better, but nonetheless there is no complete uniform encircling of the shroud collector plate nozzle by argon injection. So there is a problem here, and that problem is going to be much more serious when we are talking of this kind of a shroud design. So to understand the air-water, air oxygen distribution in actual shroud system, so you have a collector nozzle, and we have a little shroud. There's a section of it which is shown here. So gas is being injected here, and we want to find out in this annular dome what is the distribution of argon and air, and we have developed a model also, because this water model results may not be exactly applicable because the temperature effects, etc. is not there. So we have a species conservation equation which considers of 2 species distribution in the system, air and argon. We have an energy conservation equation which takes into account the flow of gas in a hot shroud, because the shroud world temperature could be something like 900 degrees centigrade. Then we have a turbulent flow because the Reynolds number is high, and we have a 3-dimensional Navier-Stokes equation, and then we have calculated the flow distribution here and try to find out that what is the profile of argon, how much argon, what is the distribution pattern of argon around this collector nozzle. And if we do to compare the 3 different cases, this shows us, this is the worst case, where it shows the distribution of argon. And what is this distribution? This distribution is somewhere along. So you have a circumferential line, and you can see it is theta is equal to 0 to theta is equal to 360 degree. Okay, and it is somewhere here. If you pick a line, and on this line, along the circumference, if you move on, how is the variation of argon? And it shows among the 3 designs, there is quite a bit of difference. Okay, there is, in this particular case, we have barely 15% argon remaining, at that particular height. We have 85% oxygen, and the best design that we have is something around 80% argon and 20% oxygen, or 20% air. And this figure, whether you carry out isothermal, which is yellow, or non-isothermal, has been reflected clearly. So which it tells us that water modeling investigation indeed, gives us a reasonable idea, albeit qualitatively, okay? And it shows us, the differential features of the three design has been brought out very nicely by the numerical computations. Now, most interestingly, now at this stage, we understood that, there exists considerable scope to improve the argon distribution around the shroud collector plate nozzle. So now if you try our design, which is a new design, okay, and that new design gives us a significant enhancement, almost 95% of it is going to be. So this is, while these lines correspond to one single line, this is the volumetric average of argon in this annular region, okay? So the total residual oxygen here is barely 5%. So it shows that the design 4 and design 5, which had been involved in our laboratory by carrying out a large number of computational trials, essentially tells us that the efficacy of argon distribution around the shroud collector nozzle can be considerably increased, and we can get almost the entire space filled with argon. That's what is desirable. And therefore, we conclude here that gas distribution efficacy can be improved by changing the gas delivery designs. I'll show you an animation, and then you can see, for example, how does, for example, this blue essentially indicates that this is filled with air at time t is equal to 0. And now we have, when you start blowing argon through it, so argon is red, and you can see here, for example, this is one of the existing designs, and you can see the animation that, we don't get anywhere red except for this inlet nozzle, okay? And if we plot here also, this is our existing design, new design, and you can see the rotational effect here. We have a tangential port here, so there is a rotation, and you can see the buildup of the gas. And if you see, there it is green, which essentially means about 40–50% of it is going to be argon, and 50% is going to be oxygen. On the other hand, if you look at the new designs, of course, at this particular surface, you have, the air is present, so that's why you see some, blue region, but bulk of that annular space between the collector nozzle as well as the shroud is red, which essentially indicates that this is, essentially filled with argon. So whatever, we have found out computationally and experimentally by water modeling can be depicted very nice through this animation. And the summary of it is shown here, that you have two different cases, the existing design, and whether we go here at the lower part, which is this, at the intermediate part or at the top part, the existing design shows that there is nowhere it is red region, nowhere there is a little bit of argon, most of it is air. On the other hand, the new design shows us that it is, at the bottom part, it is going to be red, or argon, at the intermediate part is also going to be red, and somewhere at the top, we can have about 90–95% of argon, which is present there. So it shows us that by, changing the gas design facilities, which are very simple, and this is not rocket science, this is high school level knowledge again, by, reorienting the gas ports, the number of gas ports there, orientation, etc., and one can really improve the distribution of argon around it. So we have found out this in the laboratory. We have a design available to us, and now we are knocking at the door of the industry that, and the industry has to come forward now to do this part. And we found, fortunately, a nice partner, and that's what, is this particular work. Next two slides is going to be. So we found out a refractory manufacturer who was willing to make this refractory artifact, the ladle shrouds. We found a steel plant with the, which were trying to minimize their atmospheric air absorption through ladle shrouds. So they are also keen to incorporate this shroud design. So we made about 50 shrouds, brought them to our laboratory first, and then we wanted to be sure that they could incorporate our design precisely. Having given the final, clearance, 50 shrouds are manufactured by the refractory makers and shipped to the steel making industry, and they are deployed in trials. The trials were done in two different phases, one during the lockdown period, that's November 2020, and the other during February 2021, which is still ongoing. And we monitored many things, including nitrogen absorption. All other process parameters were identical. And if you look at the nitrogen What are these lines here?
I think somebody shared their screen at some point.
Okay. So this is the existing. I have kept deliberately. There are three figures. There is a campaign one figure. This is the ongoing campaign figure, and this is the existing shroud practices. Okay. And this is the nitrogen pickup in Tandish. I kept this axis deliberately same. These are 60 ppm nitrogen. We have got about maximum of 55 ppm. And you can look at the existing practice, where the average is about 25 ppm, and look at the scatter. Okay. And now you go to the new campaign with our new shroud design. So from 24.5, it has come down to 9 ppm. We have only done 9 trials. These are the 18 points, the same set of points, where we have taken bullet Bloom 2 as well as Bloom 3 data. And that's why we have about 18 data sets. And that's why you see that this pattern is being replicated here also. So it's the same set of data, but with respect to Bloom 2 and Bloom 3. But this also essentially indicates that we have about 12 ppm of nitrogen pickup, because the data set is small. So I think this 12 ppm can go down further to 8, 9 ppm, once we have large number of data and so on. Now we must understand that at this particular stage, we have just changed our ladle shroud. There are 2 more things. The mechanical issues need to be sorted out, and the argon flow rate. And I am sure once we incorporate these 2 additional aspects into steel making practice or the transfer operation from ladle to Tandish, this figure can come down to 1 to 5 ppm, which is the global average. And that is the real challenge. And on that, we will be working in the next couple of months when I visit the industry. So summary is, existing ladle shroud inert gas delivery systems are largely inadequate, that we have demonstrated through physical and mathematical modeling, and do not ensure homogeneous urban distribution, that also shown. And we have found out a design of water model, design of ladle shroud gas delivery systems, which works out well, okay, and ensures better argon distribution around shroud collector nozzle. And we have demonstrated this by conducting and the industrial scale trials. And it is there I see that the proactive role of the industry is extremely important, and that trust needs to be developed over the years. And it doesn't happen, as I have been saying throughout, overnight. So I've been very happy that these ideas could be crystallized or given final shape by conducting trials in the industry, where industry has a big role to play. I just want to show that what are the ongoing projects that we are trying to do. One project is, because I'm trying to look for an industrial partner. You know that in continuous casting, we have Bloom cast, we have what is known as an electromagnetic starter to introduce stirring into the Bloom casting mode. And the recent trend is that this is very expensive affair, to have a electromagnetic starter. If you have a gyro nozzle, with which, it's a specific design nozzle, which we can impart the rotational flow, which is more or less similar, which is introduced into hot steel by electromagnetic stirring. So we are trying to design an optimum gyro nozzle for delivery of molten metal into continuous casting mode. So it's a combined magneto-hydrodynamic and reaction engineering modeling. And we want to extrapolate that electromagnetic flows into, the domestic steel makers, particularly the induction steel producers, producing sector, whereby we can tell them what is the rate of decarburization and what is the extent of nitrogen up by the melt, and so on and so forth. We would like to further explore, the concept of tangential gas-driven gas inlet ports in the context of EOD converter. Again, also we are trying to look at, one kind of an industry support, and the objective here is to basically introduce a swirling flow in the converter, whereby the tap-to-tap time can be significantly reduced. Huge generation of revenue for the stainless steel making sector. And this is the first and perhaps the last iron making project that I'm trying to deal is to simulate, the refractory UV phenomena, which is again, a heat transfer, mass transfer fluid dynamics controlled phenomena. And here also, fortunately, we have a supporter and a Calderis refractories who is interested in supporting this activity. So these are some of the works that we are trying to do. And I hope, before I retire, this work will see the light of the day and will contribute to the welfare of the steel industry. I now come to the finishing slides, and this is a philosophy which I resonate very much. I sing in the same tune, and this is, I have it posted in my laboratory as well. A quote by Professor Alex McLean, and who talks very nicely about the industrial research. And I would take this opportunity to read it verbatim once more, because I enjoy reading it again and again, and which has been so close to my heart as well. The preeminent aim of collaborative activities between our educational institutions, industrial organizations, government funding agencies, and professional societies like IIM is to ensure the availability of high-quality people who not only understand the fundamental aspects and practical implications of their discipline, but also are fully equipped with essential skills of communication that will enable them to participate throughout their career in this most challenging and satisfying activity, the science and technology of steel making. And so, with these words, I would like to conclude my talk. And this is our effort to build confidence beyond the boundary of IIT Kanpur. This is a water modeling exercise. And the work that I have presented today could not have been possible without the assistance of all my graduate students, my doctoral students. And I sincerely admire their sincerity, their diligence, and on top of that, helping me to structure this presentation in a elegant way. Thank you very much.
Thank you very much, Professor Mazumdar, for a wonderful and illuminating talk. We have some time for questions, so I would ask you to raise your hands. I see some questions in the chat box. One, Mr. Venkateshan has asked this question: can you comment on CO2 utilization in the steel making process to mitigate emission?
Comment on CO2 utilization or some questions.
So there is one question from Venkatesh, Mr. Venkateshan, who is asking that can you comment on CO2 utilization? I don't know whether it is connected, but this is a question that is.
See, this is, I think, Amaranda, is a big topic, okay? And I have really not worked, on any project related with CO2 mitigation in industry. I have worked, of course, on heat recovery, which is related with heat recovery from sensible gases, which contain also CO2, particularly in steel industries. But per se, I have not extensively worked on CO2, so I think there are experts who can opine. It is not good for me to claim that I know everything. And perhaps, I can certainly discuss. There are certain sections written in my textbooks also, and there are, plethora of knowledge available on this topic. So I would refrain from speaking anything on this, knowing that there is a highly qualified people in the audience, and lest I make some mistake. So let's go on. Go on.
Dr. Balamurali Krishnan, please go ahead. Actually, you can just ask the question by unmuting yourself.
Thank you, Professor Singh. Thank you, Professor Mazumdar. It was a fantastic talk. We really enjoyed listening to the whole of it. And I particularly like the last quote by Professor McLean. I think it's very, very relevant in today's times. And I think, sir, you should popularize this quote now amongst our people. Sir, one general question which I had was that, there is a lot of confusion, including many times within us at the defense labs and many other R&D institutions. And when we talk to industry, there is, and I'm asking this based on your really large and diverse experience with multiple industries, sir. The question is, how do you balance this pre-competitive research? What you can do in publications, for example, what you can write papers with your students versus protection of IP for a particular company that may be sponsoring your work and sharing the data with you. And this data sharing is becoming increasingly important, as Professor Singh will also appreciate. We are trying to put some ICME kind of effort. And where, how to basically balance between these two, sir. If you can throw some light on it, I'd be very thankful.
I think, I do not name an industry explicitly. This is the first thing. Of course, I take permission because all my industry papers are actually co-authored by a person from that industry. I have never deprived them. They are funding agency. So they, have one or two people from industry, and they sell gold medals also, papers we have people from industry. So I have never, bypassed them. I have taken permission, and very tacitly I have really disclosed the data. And as far as IP goes, I mean, I have not been looked at it, very carefully, because I am an old-fashioned Indian, and I think, I'm not much interested in making a patent myself per se. Okay, even this little shroud design, I have, a shroud design, gas delivery design. I have asked my student that if he is interested, he can go and do the patent. My job is to, solve an industry's problem. My job is, and I have not given the details of this gas, delivery designs, but some people, who are smart, who can work it out. Okay, where I have given enough indication, and it is possible to work out from there itself. So, maybe the refractory industry or the steel industry and my student will go, and IIT Kanpur will be a party. I'm not even saying that, include me as the first party or last party. I am least bothered about making patent and making money out of it. So I do not subscribe to this Western philosophy. For me, the knowledge is, I think I look at it like, you can say that Professor Mazumdar, you are becoming nostalgic or philosophical, but that's the way I am. I am, I have given, my first patent is, of course, is filed by one of my students at JSW. I don't know what is the fate of it, neither I'm interested to know. And same is here with this study also, and there have been similar such cases in the past. But yes, when I show data explicitly, I do not name an industry, because there are connotations of publication of data with regard to a given industry, because many people, including the end customers, will be reading, and that could sometimes prove to be very fatal.
Thank you very much, sir. In fact, I very much enjoyed your comment on the IP part. Personally, I would agree with that 100%, but sometimes there are institutional obligations on both sides, from the industry side as well as from the our own R&D kind of side. So that is why I was curious in asking this question. Anyway,
Yes.
Thank you very much, sir.
Yes, my pleasure.
So there are a couple of more questions. I think one, Mr. Pranjal Chauhan, he's asking that is it possible to improve the level of turbulence at the nozzle inlet? This can improve the distribution of argon in the system. I don't know what he means.
No, I think I would say that, you see, it is logical. I mean, if you have one single port and you have multiple nozzles of equal-sized nozzles, the elementary fluid dynamics tells you that you cannot have a uniform distribution. From the first two ports, which are close to the inlet, maximum amount of gas will flow out. So no matter how you play with the turbulence and all, so you have to, change your mindset and look at the issue from different angles altogether. So although we have not explicitly tested this philosophy that by, incorporating more turbulence or less turbulence at the nozzle, and we wanted to have the same kind of devices, same kind of fabrication technique, same kind of, material, not change too much. Otherwise, the industry will not do anything for us. They want the path of shortest, least resistance. So we have done, minor adjustments to the gas passage and the port designs, and obtained the desired or the beneficial results.
And there is one
But
more.
there may be many theoretical solutions to the problem, which may not be practically viable.
There is one more question on the technical part of it, is from Shivam. He's asking, is it possible to reduce slag metal interaction using submerged rod opening?
I could not read that.
So this is in the end actually. So is it possible to reduce slag metal interaction using submerged rod opening?
Yes, I think absolutely, particularly in the lead hit. For example, very interestingly, RHI has recently introduced, a disposable part of the little shroud. That means, that what we call the front end of the shroud will be almost touching the base of the tundish. And as molten metal will keep on rising, at one point of time, when the original shroud is going to be exposed, so that additional paraphernalia will get, dislodged, and then the shroud is going to be submerged. So it is an innovative design whereby the air steel interaction in the tundish has been completely dispensed with.
Dr. Agarwal, you can unmute yourself and ask a question. You wanted to ask a question, please. You are muted, Dr. Agarwal. Can you ask the question?
Just I want to ask one question. I am A.K. Srivastava from Jaipur.
Please go ahead. Please go ahead.
Okay. I just want to ask, I must congratulate Dr. Mazumdar for the preliminary talk on this aspect of continuous casting. But what I could gather is that this study was conducted by PhD students, and they must have done it in the laboratory scale only. Whether these results of studies have been implemented in any of the steel plants or any of the continuous casting plant, I just want to know. Or it will just remain like a study of for academic purpose.
No, sir, this is not for academic purpose. As I said, the first two set of trials results I have shown, which the industry, which are industrial trials, which have given significantly enhanced, performance as far as nitrogen absorption is concerned. Now, I will be visiting that industry and giving green signal in the next month, and then the bulk production, all lateral shrouds are going to be displaced. So right now, it is a pilot scale project. Initially, the trials have been made, encouraging results have been obtained, and industry now wants to know from me that should they replace all the shrouds in their two casting shops.
Our Tata Steel, Tisco, and Steel Authority both have got their research and development center. One is NML and other one is the RDCIS Ranchi. So have you taken them into confidence while conducting this study? Because unless they agree, you cannot implement your results of study in any of the steel plants.
No. There are, other than Tata Steel and RDCIS Steel, there are 100 steel plants in the country, sir. Okay. You must understand that.
But they are the largest.
The huge sector of special steel industries, and as I have been saying, that I'm very touchy about the whole thing. Big industries have everything. It is that particular sector of industry, special steel plants, which are going to be the pivot for the Make in India program, because they are the ones which produce the state-of-the-art steel, not the typically what you call structural steels, various grades of high-end steel and automotive grades of steel. So it is that sector which do not have any R&D facilities. जिसका पास पैसा है उसको पैसा देने से क्या है? जिसके पास पैसा नहीं है उसको पैसा नहीं है.
Whatever it is, but the benefits of your research should also be our steel plants sale and.
That is not my headache, sir. I have made this presentation. I will implement into the industry. Refractory industries will start marketing it, so it will get automatically. I don't have to do it. My contribution is the intellectual contribution. I cannot go and do the door-to-door vendoring. Okay. So for that, there are industries. Refractory industry is always a part of this. I'm not naming it, but that refractory industry is now going to push this design in different steel industries. So it will happen automatically. I don't have to do anything.
I think Dr. Agarwal is not able to ask questions for some reason. He has
Thank you,
Mazumdar. So I think we will just have this last question. Dr. Agarwal, are you able to come? Can you ask the question, Dr. Agarwal? I think that he's not, Dr. Agarwal is not able to, we are not able to hear him. Dr. Shukla has asked this question that academic institutions R&D, or what is your opinion on research requirement by academic institutions and R&D on raw materials front? And don't you think that we lack our potential in high temperature metallurgy research and development? So I do not know that is connected with this current talk, but if you have any questions.
I think, I would say with regard to the Professor Shukla's statement that there is quite a bit of research, particularly on the raw material front being done at NML Jamshedpur, as well as, this regional research laboratory, which of course is IMMT now, Bhubaneswar. But I think there are, people like, I think there's a professor, Nikhil Dhawan, who is working on raw materials at IIT Roorkee. all, and I will certainly say that we do not have critical mass. That is true with steel making also, iron making also, because these are, kind of old-fashioned areas. So we have manpower shortage, but I think if there's a good collaboration, as I say, I could do so much because I could join hands with many people. I got good students at the fag end of my career. I got support from steel industries. I got support from ministry, and that's how I could deliver so much. So I think we have to come out and we have to, try to form bridges, and then only possibly together we can deliver. As an individual, one person cannot do. And if I think that everybody will come to me because I'm a great professor, I think that's not going to happen.
I don't think we are able to hear Dr. Agrawal. There is some audio problem perhaps. So, and we are about now 6:14, 15. So I think we would, Dr. Agrawal, are you able to hear?
Are you are able?
Please go ahead. This is the last question. Yeah, please go ahead.
Yeah. I must congratulate Dr. Mazumdar and his batch students in the very vibrant lab which he has in IIT Kanpur. I was lucky that I had a glimpse of work which was going on. This is a problem and a solution of a great industrial research. Dr. Mazumdar, I have got a small query since I am from an industrial R&D background. See, every steel plant and every continuous casting machine has a different supplier, and equally umpteen number of suppliers are there for the subsystem also. So in that case, suppose let's say Bokaro has a 3 continuous casting machines. They have a different setup. So suppose they want to investigate on this, that means that every setup is to be investigated first separately. Something like a pathological test is done on the individual person, and then you will suggest some sort of a customized solution for that particular shop or that particular machine. Is this correct?
Yeah, I understood your question. So let me say, suppose you have a TAN dish. Okay. Now you want to improve inclusion flotation from TAN dish.
Correct.
So I can, if I am a good doctor, I can look at the patient, his history, and then I can suggest that, before I get all the tests done, etc., you can try these medicines. Okay. So initially, that's what I said. The insight of a modeler is of great value in this whole exercise. Okay. And then with my experience, with my expertise, I can suggest that in your TAN dish, you do this. Then you make, measure the dissolved aluminum content changes in that, and then you will see whether the two things work or not. So the solutions may emerge purely from experience and intuitions of the modeler itself, which is backed by solid scientific knowledge like previous modeling exercise results. Okay, so it is not that I will arbitrarily do anything and then do the experiment. So I have some basic guidelines in order to incorporate the design modifications in a TAN dish. And then, of course, to convince the industry, I will make measurements from both the TAN dishes and demonstrate before them that, look, whatever I did is correct.
Very good. Very good.
And as I say, that the day I have a model which can, take into account air invasion, nucleation, growth, etc., then I can do those calculations exactly beforehand itself by, incorporating both reoxidation and flotation. And then that I have a solid scientific base to advance, on the basis of which the design modifications will be done. And then, of course, to substantiate, we have to have supplementary measurements on dissolved aluminum or dissolved calcium or dissolved silicon and so on and so forth.
Yeah, very good. Thank you. I mean, I thought when I share this information with the some of the steel manufacturers, my parent obviously is Steel Authority of India Limited. Maybe I'll mention a word which you just now spoken. First, a patient is to be looked into, is to be analyzed by a doctor, not a medical doctor, but Dr. Dipak Mazumdar, and a customized solution can be worked out later on. It's not basically some sort of a, off-the-shelf solution like a vaccine from coronavirus. It is not that. It's not a universal solution. Very good. Thank you, doctor.
Okay, pleasure.
I'm sure there are many more questions, but in the view of time limit that we have, I would like to thank Mr. Mazumdar for the wonderful talk, and I would now request Dr. Nilesh Gurao, the member of our executive committee, IIM Kanpur chapter, to propose a vote of thanks.
Matter of great pleasure for me to give a talk and present a vote of thanks. I'm sorry for this, but it's indeed a matter of great pleasure for me to present a vote of thanks for this event in front of all the dignitaries. First and foremost, I hope all of us agree that we were lucky enough today to listen to a wonderful lecture by Professor Mazumdar, who keeps keeps continuing to inspire all of us as a great teacher. Be it his books or his NPTEL lecture or his day-to-day conduct. He's a true academician, and it is always a pleasure listening to you, sir. And indeed, you showed us very nicely that how rigor in mathematics accompanied with experiments, the water modeling experiments and the data obtained from the plant can be combined together to obtain much better insight, which can not only improve the performance of the steel plants, but also generate wealth, which is very important for a country like ours. Secondly, I would take this opportunity to thank Professor Amol Gokhale, Chairperson IIM, for gracing this event, Dr. Balamurali Krishnan for starting this webinar series, as well as IIM headquarters for making this event possible. I should also thank the IIM Kanpur chapter, Professor Amarendra Singh, and the entire IIM Kanpur chapter team, including the IIM Kanpur student chapter, for making this event a grand success. And finally, let me thank each and every person present for this seminar who have attended the seminar and participated by asking questions and gracing this occasion. So thank you very much for your kind attention. Thank you.
Yes, we close our meeting. Thank you. Thank you, everybody, for participating.
Thank you. Thank you.
Thank you. Thank you, sir.
Thank you. Chalo,